Hey y'all, we are Memphis Community University and we're back for another Calculus Done Wrong lesson where we wrong calculus before calculus wrongs us. Today we're going to be concluding our differential equation unit, focusing on the AP exam and the free response questions in particular. So today how we're going to conclude is we're just going to do all the random little things on these free response questions that we haven't covered in previous videos. Keep in mind that the most important thing on a differential equation free response question, of course, is the separate and integrate process. So go back to watch that video if you want the big meat of these questions. But we do like to answer every single question correctly, or at least have a chance to. So that's the point of this video, just a bunch of random little topics. Usually I go through a sort of a general overview before I start the question, either introducing a formula or a method. But in this case, because again, the questions are quite random, they don't have anything to do with each other, except that they involve differential equations. So I'm just going to do each question one by one and not talk about them overall. So let's get started. Again, this is just the random stuff of differential equations. So differential equations extra. So we're going to talk about a variety of questions in this video. We're going to be talking about tangent line approximations, implicit differentiation, L'Hopital's rule, but we're going to start off with a very easy question. dp over dt is equal to something like 40 minus p. And let's say that in this question, p represents some population. So p dt is the rate of this population. So just remember that, again, the differential equation that's given is the rate of the population, how fast it's growing at a certain population or time. So if this is the given, then they ask a very simple question, like what is the rate that the population is growing? When p is, for example, let's say 10, let's put some units here. Let's say that population is in terms of people, I guess. Let's say t is in terms of years. So what we're going to do is we're finding the rate that the population is growing when the population is 10. Well, again, because this is already the derivative, remember that the given itself, the differential equation, is the derivative itself. Rate is a derivative, so usually you have to find the derivative, but in this case, all you have to do is plug in the number. So it's a very easy question. What would it be? Well, it'd just be 30. So it'd be 30 people per year. So whatever we're looking at, maybe a small town, as the population, when the population has 10 people in it, that means that I'll be growing at a rate of 30 people per year, because it's the quantity, the unit of the population divided by your time unit. But again, the main thing to keep in mind in this first example, which is very easy, usually people don't need to have this as an example actually, because it's very logical. Just remember that this thing is the derivative, so when you need to plug in stuff, you just plug it in. But let's do something harder. Let's talk about implicit differentiation in the context of these questions. So we're going to have implicit differentiation. And we're going to use implicit differentiation to answer some questions about the math of these differential equations. So let's say we're doing implicit differentiation. Of course, if you want to watch our old implicit differentiation videos, that's certainly recommended. But we should be able to do these questions without those videos. So keep in mind that implicit differentiation, the one we're used to the most, is derivatives of y's. So for example, when you're taking the derivative of something with y, because y is a function of x, you need y prime. So the derivative of y cubed isn't just 3y squared because of the power rule, it's 3y squared times y prime. So this is the same idea. You have a differential equation that's given, for example, dw over dp, for example, and we want to take the derivative of w cubed plus 5p. So keep in mind that there's going to be different variables in these questions, so you just want to get accustomed to it. That's why it's nice to know the general form dy dx. So what's the actor who's playing the role of y and x in this case? Well, because it's the top thing, w, usually it's a capital letter if we don't use y. This is going to be the dependent variable. This is going to be your function value variable, similar to y. What's going to be the independent variable, the variable you're taking the derivative with respect to? That's going to be your bottom variable, so that's in this case p. So for example, if we're given this differential equation, which is first derivative, and we want to find the second derivative, well, all we're going to do is take the derivative, but we have to be careful with implicit differentiation. So then what's the second derivative, which is notated, of course, like this? Well, what's the derivative of 5p? Well, because p is like the x in this case, the derivative of 5p is similar to the derivative of 5x, which in this case, of course, is 5. So it's going to be plus 5. You don't have to multiply by any sort of weird derivative because you're taking the derivative with respect to that variable. The derivative of w cubed, though, is a little bit stranger because w is playing the role of y. And just like the derivative of y cubed is 3y squared times y prime, the chain rule of that times y prime, because we have to multiply by the derivative of the inside function, and the inside function is y, we do need to account for that in the same way for this. So what's the derivative of w cubed? You can imagine that a lot of students write 3 times w prime, or 3 times w squared, because they do the power rule, they take the 3, drop it to the front, subtract 1 from the exponent. All of that is right, but this answer is not complete because, again, w is a function of p, so you have to multiply by the chain rule. So you have to multiply by the derivative of w, which is dw dp. When you have this, because we had no formula for dw dp, one thing we can do is replace dwp with this so that we can have our answer in terms of just w's and p's and no derivatives. So it's going to be 3 times w squared. And again, dwdp, which came from the chain rule, implicit differentiation, will replace with this. So it'll be w cubed plus 5p. And ultimately, you have a plus 5 at the end. So this is the second derivative in terms of w and p. Again, you're taking derivatives and not integrals, so it's not the hardest process in the world. All you have to remember is that when you're taking the derivative of the dependent variable, the variable on the top, you do need to employ implicit differentiation. You need to multiply by the derivative of the inside function, which would just be w prime, or another way to say that is dw dp. So let's do another similar question where we have this sort of idea, and we're going to answer a shape of curves question. So let me erase this. So let's see what we got here. So let's do something like, let's say we can just choose a random number, random letter, D, and then we'll have ds or something. And then we're going to have this given, which is 6c plus 2. And what we're going to ask is the function c, which is the solution to the differential equation, is this concave up or concave down? When c is equal to 3. So just like normal, when you see concave up or down, what you want to do is you want to immediately find the second derivative. So we're going to take this function, because we're already given the first derivative, all that's required to find the second derivative is to take one single derivative. So let's take that second derivative. d2 squared over ds squared. So you can imagine that a lot of students look at this and they're like, oh, this looks like one of the easiest derivatives I've ever taken. It's just 6, because the derivative of 6x is 6. The derivative of plus 2 is 0. But unfortunately, that is not a correct second derivative. If this were 6s plus 2, then that would be the derivative, the second derivative, because s is playing the role of x. Because s is on the bottom, dy dx, x is usually on the bottom. Unfortunately, c is like y. So what's the derivative of 6c? It's not just 6, it's 6 times the derivative of c. Like the derivative of 6y is not just 6, it's 6y prime. So in this case, what's the derivative of 6c? It's not just 6, it's 6 times dc ds. The derivative of c itself. Again, notice how tricky this is. If you're not being careful, it is very easy to write just 6. Now what we're going to do is we're going to replace 6c plus 2 with the derivative, because it says dc ds. This says dc ds, so we can replace it and substitute in. So it's going to be 6 times 6c plus 2. Finally, we're going to plug in 3. Notice that when we plug in 3, we're going to get 6 times 18 plus 2. Doesn't matter what this actually is. I believe it's 120 if I can do math correctly. But all that matters is that it's positive. So in this case, we have a concave up function because the second derivative is positive. But keep in mind that the easy part is just knowing to take the second derivative because we have a concave up or down question. But the harder part is to recognize, oh, when I take this derivative, I do need to employ implicit differentiation, because when I take this derivative, the derivative of 6c is not just 6, it's 6 times c prime, or dc ds. And that's how this works. So again, It is a pretty tricky question, but hopefully you recognize that if you can take the derivative correctly, you'll be good to go. So let's do another question involving shapes of curves that is similar to this. So let's say we have this. Let's say we have an initial point this time. So let's change our variables. Let's have d b over dz. Let's say we have, I'm not sure what I want to do. Let me think for a second. Let's have b squared minus z. Let's say we have an initial point of 2. By 2, I mean 4, comma 2. And then we want to know whether this point is a relative min or a relative max. So relative min or relative max. Where this point is on the function that satisfies this equation, so it will be on our b function, so it will be on b of z. So what we're wondering is that on this point, if this is a point on this function, is this point a relative min or max? So let's try to answer this question. First off, in your sort of normal relative min or max sort of setup, what you want to do is you always want to draw the sign chart of the first derivative. If it goes from, f prime goes from negative to positive, that is a rel min because you're running downhill and then uphill. If it's a rel max, you'll be going from f prime positive to negative. Unfortunately, there are some cases where you cannot do the first derivative test, and this is one of the main examples. I would want to draw the sign chart of this first derivative, but unfortunately, because it's two variables, I won't be able to draw the sign chart. So this is actually when they force you to do the second derivative test. So this question will be the second derivative test actually. So usually students need to be reminded what the second derivative test is because it's a lot more rare than the first derivative test. But what it says is you take the zeros of the first derivative and you plug it into the second derivative. Remember that it's opposite what you might expect. If it's a relative min, that means it's concave up. So that means the second derivative will be positive. So the second derivative positive goes with the rel min. Min goes with positive. That's a little bit not logical, but it's based off concavity. So if you have that rel max, which looks like an upside down U, of course, then you're going to be concave down because you're eating the floor, I guess. So a relative max goes with the second derivative being negative. So what we need to do is we need to first verify that our first derivative is 0. Then we're going to plug in this point into the second derivative. So notice that when you plug in this point, keep in mind that we're not dealing with our normal x's and y's, but because we have bz here, bz, it looks like z is our first coordinate and b is our second coordinate. So when you plug this in, notice you'll get 2 squared minus 4 is equal to 0. So that means we have a horizontal tangent line at this point. So now we can actually verify whether this is a relative min or max using the second derivative. So let's take the second derivative. So it's going to be d squared b over dc squared. And again, the main point we're doing this is to employ implicit differentiation, meaning that we need to know whether we need to actually take the derivative correctly, being careful with variables. So what's the derivative of b squared? Well, because b is the dependent variable, it's the y in this case, it's not just 2b to the 1, it's 2b times b prime, which in this case is db dt z. Because again, when you multiply it by the derivative, or when you take the derivative of the dependent variable, of the thing that's acting like y, you need to employ implicit differentiation. So in this case, it's going to be dv over dt. Then the derivative of minus z, because z is playing the role of x in this case, the bottom variable, that derivative is normal. It's just minus 1. So it's just minus 1. So what we need to do is we need to plug in 4 and 2 into all of this and see if we get a negative number or a positive number, because that would determine whether it's a relative min or a relative max. So when we plug in 4, 2, well, we need to plug it into the derivative, but we already plugged in 4, 2 actually into the derivative, we're going to get 0. So we're going to end up getting 2 times b, which is 2. If you wanted to, you could replace db dt with b squared minus z and plug it in. But because we already plugged it into the derivative, we know that it's going to be 0. So it's going to be 2 times 2 times 0 minus 1. Looks like we have negative 1. So now we're ready to answer the question. Remember, if the second derivative is negative, that means it's a relative max by the second derivative test. Because the first derivative is 0, the second derivative is negative, that means that b of z, it's opposite what you might expect, because you have a max and you're concave down, represented by this negative 1, it's negative. B of z has a relative min here. Not a relative min, a relative max, as I've been saying. Or a local max by the second derivative test. So again, what you want to do in these questions, because you're taking derivatives, it is pretty easy. You just want to be careful of this implicit differentiation business. When you're taking the derivative of variables at the top, that's like y, so it needs implicit differentiation. When you're taking derivatives at the bottom, you don't need implicit differentiation because those are your independent variables. And it's nice to review shapes of curves. How do you find concave up or down? Find the second derivative, see if it's positive or negative. How do you find relative min or max? Well, because you can't draw a sign chart of the first derivative in this case, you're forced to do the second derivative test, the second derivative test being reversed of what you might expect. Negatives go with rel min, the second derivative with positive goes with rel, sorry, I said the opposite of what it is. The second derivative being positive goes with relative min, the second derivative being negative goes with relative max. But that's this question right here. So that concludes my implicit differentiation sort of rant. It might come back a little bit later, but for now, let's switch to tangent line approximations. So I'm going to erase this. I'm going to erase this. So tangent line approximations are pretty easy. They're one of the easiest questions on these free response questions. So basically what happens is that you're going to have some differential equation. Let's use dy dx's. Let's say we have something like, I don't know, y squared plus x. And we have a function, so f of x is equal to y, is a solution to this differential equation. This happens in every single free response question. So it's a solution to this differential equation. And we also know an initial point on this differential equation. Let's say for the solution, let's say we know that 1, 2 satisfies this function. It's on this function, 1, 2. So the goal is to use this differential equation in the point 1, 2 to approximate, that's why it's called tan line approximation, to approximate f of something like 1.2. So that's going to be our goal, to ultimately find f of 1.2. So approximate f of 1.2. So this is tan line approximation, so let's just break down this, the wording for this. Approximation means we're not going to find the number exactly, we're just going to approximate it. So actually we're going to leave this f of 1.2 to the very end. What we want to do is we want to talk about tangent lines. Remember, the important thing about tangent lines is that tangent lines, you need two things because you're a line. Well, the first thing you need is a point, and the second thing is you need a slope. The word tangent refers to that the slope will be the derivative because that's how tangent lines work. So all we need to do is we need to first come up with the equation of the line, and then ultimately we're going to plug in 1.2. Keep in mind that, again, I avoid this weird decimal number until the very end. What I do is I plug in the point first. So let's plug in the point. So we have dy. I find the point in the slope. I find the equation of the line. Sorry, I don't know what I'm talking about anymore. Thinking about something else. But again, I avoid the 1.2 number. I find the equation of the line first by finding point and slope, where slope is the derivative, and then I plug in 1.2 at the very end. So let's ignore the f of 1.2 and let's try to find the point. Well, the point is very easy. It's just this point right here, 1, 2. And then the slope is as easy. Again, the slope is represented by the derivative, but we don't even need to take the derivative of a function because we have a formula for the derivative. So all we're going to do is we're going to plug in 1, 2 into this function right here. Notice that there is an x-coordinate and a y-coordinate. So where do we plug in each one? Well, we were going to plug in 1 for x, of course, and we're going to plug in 2 for y. So in this case, it's going to be 4 plus 1, so our slope is 5. This gives us a chance to write the equation of the line. It's going to be y minus the y-coordinate, which is 2. I'm writing it in point slope form like I normally do, equals slope times x minus the x-coordinate. So again, all of this is review. It's just tangent lines, point and slope, where slope is the derivative. The point was given, the slope was basically given as well. All we had to do was plug in the coordinates for the point, and we found our slope. Finally, we're doing the approximation. So the approximation, again, is done at the very end. All you're going to do is you're going to plug in 1.2 for your x right here, and you're going to find your approximate for y. So it's going to be y is equal to, well, we're going to bring the 2 over, 2 plus 5 times 1.2 minus 1. You can certainly do this with decimals if you want. 1.2 minus 1 is 0.2. 0.2 times 5, that's just 1. So it looks like we have 2 plus 1, which is equal to 3. So this is going to be the approximation. Maybe we should put approximate signs. Approximate, approximate, approximate. And that's the answer. So hopefully you see that, again, this question is very easy in my opinion. It's a lot easier than separate and integrate, for example. all you do when you see the words tangent line approximation or linear approximation, don't look at the decimal number first. First find point and slope. Point will be given, slope will be given basically. Where to find the slope, just plug in the point into your derivative, which is the differential equation that's given. You'll have point slope form, and then finally plug in 1.2. So let's do another example of this. So let me erase this. Let's say we have, let's do different variables now. Let's do dh over dt. Let's say we have 3h minus 2. And we're going to ask a little bit harder of a question. First off, we're going to take an h, and we're going to have a given point just like the previous example. So let's say our given point is 0, 2 or something like that. So this is a given point. H is a solution to the differential equation. So what we want to do is we want to approximate, let's say f of 0.5, where f of t is equal to h. So h is, again, the solution to this differential equation. And then we're going to ask the second question. We're going to ask whether this approximation is an overestimate or an underestimate of the actual value. So over or underestimate. So they ask overestimate and underestimate questions throughout the AP exam. Usually they ask it based off Riemann sums and integrals. But in this case, when you have tangent line approximations, it's going to be based off concavity, as we're going to see. So first off, what we need to do is we need to find a point and a slope where the slope is the derivative, just like the previous example. So let's start off. Well, the point again is very easy. It's already given. It's 0, 2. Then we need to find the derivative. So the derivative also isn't that bad. We're going to plug in 0 and 2 into this function. Keep in mind that we don't want to plug in 0 because 0 is the time coordinate or t coordinate. So that's t, h is on the top. So when we plug this in, we're just going to plug in 2. 2 times 3 is 6. So let's actually do that. We're plugging in the point. This is vertical bar notation, meaning I'm going to plug in this point, 0 and 2. I don't plug in 0 because there's just no t's in this thing. All I do is plug in 2. It's going to be 3 times 2, which is going to be 6, minus 2, which is 4. So now I'm ready for the equation of my line, just like normal, point slope form. Y minus the y coordinate equals slope times x minus the x coordinate. I'm going to use the actual variable, so I'm not going to use y's and x's. Let's use h's and t's. So now we're ready for the approximation. So again, this is exactly like the previous question. To approximate using tangent line approximation of a value that you want, what you do is you use your original point that's given, you find your slope by plugging in the point into your differential equation or the derivative. So in this case, it's going to be 4. We have this nice little line, and finally we plug in 0.5. So when we plug in 0.5 and solve, notice it'll be h is equal to 4 times 0.5 minus 0, that's of course is 0.5, plus 2. So it looks like it's going to be 4 times 0.5, that's 2, plus another 2. Looks like my approximation is going to be 4. So that's going to be the answer. What's the approximation? 4. Again, we did the same thing as normal. Find the point, find the slope, take the derivative that's already given, take your point and plug it into that derivative. You'll find the slope, write your slope and point slope form for the equation of the tangent line. Finally, plug in 0.5, the weird decimal number. Don't plug it in at the very beginning, plug it in at the very end. We do have to answer this question about overestimate and underestimate. And what it's based off is actually concavity. So what you do is you want to take the second derivative. This is a nice review of our previous statement that we talked about when we talked about implicit differentiation. So let's take the second derivative here. So I'll tell you why we're taking the second derivative after we take it. So in this case, when you take the derivative, again, be careful, the derivative isn't just 3, it's actually 3 times dh dt. Then we're going to replace dh dt with what it is, 3h minus 2. So it's very easy to write that the derivative is just 3, but because h is playing the role of y in this case, we do have to implicitly differentiate like we did a few minutes ago. So in this case, it's going to be 3 times 3h minus 2. Finally, we're going to plug in the point. We're going to plug in 0, 2. Looks like we're going to plug in 2. Again, we don't plug any t's in. we don't plug in this number t because we don't see it. But when we plug in 2, looks like we're going to get 6 minus 2, which is 4. 4 times 3 is 12. All that I care about is that it's positive. So now I'm ready to answer the overestimate or underestimate question based off that I know that this is positive. The second derivative positive means that your function is concave up. So notice that if I draw a generic concave up function, which is something represented like this, like a u, notice that anytime I draw a tangent line to this function, so like let's say I draw the tangent line here, or let's say I draw the tangent line here, or let's say I draw the tangent line on the left side, notice that no matter where I draw it, the tangent line is always under. So because our second derivative is positive, that means our function is concave up, like this function right here. So the tangent line approximation, which is represented by this number right here that we found, 4, is going to be an underestimate. Because anytime you draw a tangent line to this function, it's going to be under. So the answer to this question will be underestimate, not overestimate. So that is a quite lengthy question. Keep in mind that if this is asked on the AP exam, it'd probably be 2 parts. They would first ask you to find the tangent line approximation, then they would like you in the second part to determine whether that was an overestimate or an underestimate. But let me try to review what we did. So again, the givens were this differential equation, this point, and we wanted to approximate f of 0.5 or 0.5 on the curve. So how we did that was tangent line approximation. We found point and slope, where slope was the derivative. The point was given to us nicely, and the slope was also basically given to us. All we had to do was plug in. We didn't have to take a derivative because the derivative was already given. When we plugged in, we ended up getting 4. Then that gave us the equation of the line using point slope form. H minus this, 4 times this. Then at the very end, only at the very end do you plug in the weird decimal number. In this case, when we plugged in 0.5, looked like we got 2 plus 2, which is 4. So that was our final approximation. Finally, they asked us another question, which is whether this was an overestimate or an underestimate. In this case, this was an underestimate because what we did is we took the second derivative, being careful with implicit differentiation. So the second derivative wasn't just 3, it was 3h prime, or 3 times dh dt. And we saw that the second derivative was positive. And with the second derivative being positive, that means our function is concave up, which means that our tangent lines, no matter where you draw the tangent line, will be underneath the curve. So that's why we have an underestimate. And that's how you do tangent line approximation questions. Let's do one more that's similar to this, where we use tangent line approximation, but not everything is given to us. So I'm going to erase this, but this is the nicest question. This is a question that would maybe give you 4 points on an AP free response question, because again, it'd be 2 different parts. Tangent line approximation, find point and slope, where slope is the derivative, plug in the weird decimal at the very end, and then also this overestimate, underestimate business based off concavity. But sometimes they ask, maybe in the multiple choice question, another kind of tangent line, or maybe on college level questions. But what they would ask is try to approximate 27.5 using tangent line approximation. Let's actually not do 27.5, let's do square root of 25.5. So basically what happens is, it's the same idea. What we're going to do is we're going to find a tangent line, we're going to find the equation of the tangent line, finding point and slope, where slope is the derivative. Then we're going to plug in this weird decimal number to approximate. So imagine you didn't have a calculator, so you wanted to have a general sense of what is the square root of 25.5, but you didn't have a calculator, so all you have is math. So what you do is you recognize that I know a square root that's nearby 25.5. Hopefully you see that it's just the square root of 25. That's where we would change it from 27, because I know the square root of 25, it's just 5. So what you do, just like the previous examples, is you avoid this point right here, and you form point and slope, where slope is the derivative. Don't look at this weird decimal number. So what's the point? I have to come up with a point in this case. It's not given, but it's the point nearby this number where you know the function. So the function is square root of x. Maybe we should list that out. So that's actually the first given that we have to recognize, that the function we're dealing with is square root of x. So when I choose the point, the x coordinate of the point, I'm going to choose a number that's really close to 25.5 that I know. So it's going to be point. Whose square root do you know that's close to 25.5? Of course, it's 25. So we have 25. Then we need a y coordinate. Well, we're just going to plug into the function. Square root of 25, of course, is 5. Then, just like normal, when you're doing tangent lines are points and slopes, where the slope is the derivative. So I actually have to take a derivative in this case. I'm going to write this as x to the 1/2 because that'll allow me to take the derivative a little bit more nicely. What's the derivative of f prime of x? Well, that's going to be 1/2 x to the negative 1/2 using the power rule. Taking the 1/2, dumping it to the front, subtracting 1 from the exponent. 1/2 minus 1 is the same thing as 1/2 minus 2/2, which is negative 1/2. Finally, I do want the slope at this number at this point right here, so I'm going to plug in 25. We of course change things to fractional exponents in order to take the derivative more easily, but once we need to maneuver things algebraically, it's nice to rewrite it as a fraction. So it's going to be 1 over 2 times 1 over the square root of x. Finally, we're going to plug in this 25 to find an actual slope. So f prime of 25 looks like it's going to be 1/2 times 1 over the square root of 25. Square root of 25 is still 5, so this is going to be 1/2 times 1/5, which is 1/10. So this is the same thing as the previous example, except we had to come up with all of our guys, but it was still the same process. Point and slope, so this was slope, where slope is the derivative. So it looks like we're ready for the equation of our line, the equation of the tangent line. So it's going to be y minus the y coordinate, 5, equals slope, which is given by the derivative, 1/10, times x minus the x coordinate. Finally, we do have to plug in our weird number at the very end, just like the previous example. You save that weird decimal till the very end, and then you plug it in. So in this case, it's going to be y is an approximate value. We're going to bring the 5 over, so it's going to be 5 plus 1/10. And we're going to plug in 25.5 minus 25. So I am running out of space, so let me try to separate everything right here. But it's not going to be too bad. Hopefully you know that 25 minus 5 is just 0.5. 0.5 is the same thing as 1/2. So if you simplify all this, it'll be 1/2 times 1/10. So it looks like we're going to have 5 plus 1/20th, because it's 1/2 times 1/10, which is 1/20th. Because 25.5 is minus 5 is 25. Sorry, 25 minus 0.5 minus 25 is 0.5, which is 1/2. 1/2 times 1/10 again is 1/20th. We're not bakers, so we're going to try to express this as a fraction. What's 5? Well, 5 is 100 over 20, so it looks like our final approximation is going to be 101 over 20. But hopefully you recognize that, again, this question is the same. The thing you want to get in habit of is right when you see the words tangent line, you want to think about two things. I need a point and I need a slope where the slope is the derivative. So in this case, we had to come up with a function itself, but the function is just square root of x. The point is the most logical x that you know that's nearby your weird decimal number, and then you forget about the decimal number until the very end, 25 and 5. Then you take the derivative, of course, because you need the slope of the tangent line. You plug in 25 into the derivative, that will be your slope. You'll write the equation of the line, and finally you plug in at the very end. So that's tangent line approximation. Those were our two big topics, implicit differentiation and tangent line approximation. Finally, we're going to do one last question, which is L'Hopital's rule. Remember that L'Hopital's rule was recently added to the AB exam, so it could be in the differential equation free response question that has occurred in the past on the BC exam. So let's write that down. So we're doing a L'Hopital question. So suppose f of x is equals y is the solution to some differential equation. So it's the solution to the differential equation. Let's write dy dx is equal to, let's say, x plus 1 over y squared. Finally, we have a point f of, let's say, 2, 3. So we, just like usual, we'll have an initial point, and in this case, this is the initial point. And what we want to do is we want to find the limit as x goes to 2 of 2x minus 4. And we're going to have f of x, and then it looks like we want 3 minus this. So this is going to be my limit. So again, this is L'Hopital's rule. It's one of the most common techniques to do limits, especially because it was just added to the AB exam. So you always want to be aware of this. Because this could potentially appear on a free response question, I'm going to do the limit the most precise way I know so that I can get full credit. You don't want to get half credit even if you know how to do the work, because they want you to write it in a very particular way. Basically, we can't write 0 over 0. So let's start off with this limit. Keep in mind, though, that sometimes all of these givens are at the very beginning of the question, and this might be part B or C. So just be aware that you always want to use the entire given for the entire free response question. But this is how L'Hopital's works. So remember, what you have to do is you have to write the limit of the top equals 0. And how do you know that this is 0? Well, when you plug in 2, you'll get f of 2. F of 2 is 3. 3 minus 3 is 0. So you have 0. Finally, when you plug in the limit of the bottom, notice that you'll have 0 as well. 2x minus 4, you get 4 minus 4 is equal to 0. So this is L'Hopital-able, if that's an adjective. You get an indeterminate form, the most famous one, 0 over 0. Unfortunately, they don't like you to write it as 0 over 0, so this is why we're doing all this work. Then, once you show that the limit of the top equals 0 and the limit of the denominator equals 0, then you write the words by L'Hopital's rule, or by the hospital. What you want to do is you want to write your original limit. So limit x is equal to 2. And only now can you L'Hopital or apply L'Hopital's rule. So when you apply L'Hopital's rule, remember to continue to write limit. It's important to write limit in a bunch of spots. Limit of the top equals 0, limit of the bottom equals 0, original limit equals new limit, where the new limit will be the ratio of the derivatives, because that's how L'Hopital's rules works. So what's the derivative of f of x? Well, it's just f prime of x. Looks like there's a negative in front because the derivative of 3 is 0. What's the derivative of the bottom? It's going to be 2. So if this were a multiple choice question, you would probably just skip to this because you would recognize that it's 0 over 0. But if it's not, you do have to find this limit and write it in this precise way. So now we're ready to apply L'Hopital's rule. Well, it looks like we have no more x's in the bottom, so all we have to do is plug in 2, f prime of 2, but we have to know f prime of 2. F is not a specific function, so we have to use the givens to find f prime of 2. Keep in mind that f of x equals y is a solution to this differential equation, so that means that f prime is equal to dy dx. So finally, we're going to use this differential equation by plugging in. Keep in mind though that sometimes people get confused because we only have one variable here. X goes to 2, but this thing has 2 variables. So I certainly know what to plug in for x. I'm going to plug in 2, but I don't know what I'm going to plug in for y. But keep in mind that we do have the given point and it does contain both coordinates. So as you plug in this x equals 2, we're using both sides of our givens. First off, we're going to plug in 2 into x, so that'll be 2 plus 1. So we'll have negative 2 plus 1. And then finally, we do know that the y coordinate is 3. So that's going to be over 9. Then we're going to divide by 2. Let's simplify this fraction. It's going to be negative 3/9 over 2. 3/9 is the same thing as 1/3. Keep in mind that 1/3 divided by 2 is not 2/3, it's 1/6. So the final answer in this lovely box is negative 1/6. So this is a very typical L'Hopital's rule question, and you want to be able to get this right because it's just a limit, and limits aren't too bad. So let me go through what we did. So you have this limit right here. So you know it's L'Hopital's rule because basically every single limit is L'Hopital's rule. Limit of the top equals 0, limit of the bottom equals 0. Then you write the lovely words by L'Hopital's rule. You write the original limit, and then you write the new limit where you take the ratio of the derivatives. Keeping in mind that the derivative of f of x is of course f prime of x. Finally, you plug in 2, just like in normal limits, you just plug in the number, and you need to find f prime of 2. Unfortunately, f prime of 2 is not given, but we know that f of x equals y, so that f prime is equal to the derivative, the original differential equation, that could be at the beginning of all of your givens. So when you plug in 2, you need to plug it into this guy right here. Unfortunately, it does involve 2 variables, but good news, we do have 2 coordinates, so you just plug in 2 for x, 3 for y, and you should be good to go. In this case, when we plugged it in, we got 3/9, 2 plus 1 over 3 squared. Finally, the resulting limit was negative 1/6. But hopefully this was useful for you. We talked about a lot of things today. We talked about how differential equations are just the rates. Then we really focused on implicit differentiation and shape of curves questions. We also focused on tangent line approximation questions. Finally, we ended with a L'Hopital's rule question with differential equations. Of course, a lot of this stuff is very tricky, and a lot of this stuff is different from each other. So it's just random units, random little lessons and things that you have to know. So if you want more practice for this, I'll link our normal Girls Teach Calculus video to the description of this video so that you can practice one of these questions. In that video, one of my former students practices questions about rate. She practices questions about tangent line approximations, where she plugs in that weird decimal number at the very end. and some with the square root things as well. Then she practices questions like implicit differentiation, which she's very careful when she's taking second derivatives if she needs to apply implicit differentiation. Finally, she does some L'Hopital rule question. So be on the lookout for that, watch that video. And this video actually concludes our differential equation playlist. Remember that we suggest really focusing on separating and integrating our first video in this playlist because that's the biggest part of these free response questions. It's over half of the free response question is that separate and integrate video. But this actually concludes our AB topics if you're going in order the way that I normally develop my curriculum. So I hope to see you next time, but I don't know if that next time will be in BC topics. I don't know if you want to go back into the past and watch that separate and integrate video. But no matter where I see you next, thanks again for watching. Give us a like and subscribe if this was useful for you as you do your differential equation free response questions. Remember that I created a total free response question a playlist just devoted to differential equation free response questions where I go from difficulty 1 through 10. A lot of that is separate and integrate, but a lot of the smaller parts are tangent line approximations or implicit differentiation questions. So check that out as well if you want more practice with this. We just have a ton of resources because we want to help you guys out as much as possible. But whatever you choose, whether to check out those videos or not, we appreciate you watching this one, and I hope to see you next time. Thanks again for watching.